So let me begin by thanking Sam and other organizers for inviting me. I've never collaborated with Russell, and yet I have always felt in a really strong way that Russell was my supporter and in my corner. And that's actually related to what I'm going to be talking about, at least when we get half or 2/3 of the way through. So, risk prediction. I'm calling this the defining problem of artificial intelligence. Not the defining problem, but the defining problem. So what do I mean by that? Risk predictors assign numbers to individual instances. And these numbers are typically interpreted as probabilities. So for example, what is the probability that it will rain tomorrow? What is the probability that X will repay a loan? What is the probability that this tumor will metastasize under the specific course of treatment? What is the probability that Y will commit a violent crime? The problem with these questions, with trying to build a function that is going to answer these, is that the very notion of what is the probability of a non-repeatable event is completely unclear. You can't, for example, give somebody the loan, see whether they repay, rewind history, give the loan again, rewind history, and so on, and get some kind of frequentist notion of probability. So what are these algorithms trying to do? What does the ideal algorithm actually do? We don't know. This is why this is the defining problem for AI. Now, complicating the defining algorithm is this question about uncertainty. So we could imagine two more worlds, which we would like to assign to Russell, but we can imagine two worlds. In one world, individual instances have probabilities only of 0 or 1. So that's the world on the left. The gold dots have probability 0 of a positive outcome, and the green ones have a probability of 1. In a different world, the red world, all of the elements have probability 1/2 of having a positive outcome. So in the green gold world, the uncertainty that we feel of, that we think about as probability, comes from a lack of access perhaps to information, or the ability to compute with what we need to compute on the information that we're given. In the red world, the uncertainty is inherent. There really is no answer yet. We don't know whether uncertainty actually exists. I guess the physicists think that it probably does, but really is the world just completely determined and we don't know the different? Yes, Russell?
Give that probability.
No, I can't. I don't even know what such a number would mean. So in the green and gold world, okay, great. Okay, so our experience of the world is only in terms of outcomes. We never see any probabilities. We only know what happened. That's all we can ever see is what happened. This person did succeed in repaying the loan, this one didn't. We don't know whether initially their probabilities were 1 and 0 respectively. All we know is these are the outcomes. So anything that we wish to do algorithmically can only work with outcomes data, like instance and what actually happened. We don't have access to the probabilities. We don't even know whether they have to be integers or whether uncertainty exists and they can be between 0 and 1. So our observations always look like the green gold world, even if the world is actually the red world. And the consequences of this is, of course, that anything we build from training data will be independent of whether real life is arbitrary or real life is Boolean. There's no experiment that we could do with our calculations that's going to make this difference. So that means that if we have a predictor F that we build by looking at real life outcomes data, we can't ask that F is actually correct on outcomes if it's in fact the case that there is uncertainty. We just don't know. An F that always says 0.5 is the most accurate description of reality in the red world, and it's not a good description of reality in the gold-green world. So this question then is, we don't know what we're trying to build, and we build something, how do we evaluate it? And this is where we are. This is what's going on right now. Now, this is, of course, not a new conundrum. People have been thinking about evaluating predictors, especially in the online setting, for decades, for at least 40 years. So long, long history in the online world, in the world of online forecasting. Predicting rain, you know, every day the forecaster says it's going to rain with X% chance tomorrow. You know, that's the situation. And starting no later than Philip David's work in 1982, and followed in rich creativity in the online setting, is a basic notion of calibration. So predictions should be calibrated in the following sense. If we look at all of the days on which the forecaster said the chance of rain is 70%, then indeed on 70% of those days it should have rained. Similarly, for all values of 70%, 30%, 40%, 29%, whatever. Now, forecasting using calibration as your measure does not necessarily encourage truth telling. Like, suppose you've been predicting along and it turns out that on the fraction of days where you were predicting 30% chance of rain, it only rained about 20% of the time. Then the next time you're really, really sure it's going to rain, you say 30% because that's going to raise your percentages for the 30% bin. So calibration has a long history and it's very interesting, but it's not exactly clear what it's doing. And this is just to give you some idea that yes, there really is a long history and a rich and an interesting history in the online world. Okay. Everything else that I'm going to be talking about today, though, is going to be in the batch world, where we are working with some training data. There is a distribution on instance outcome pairs, and we're trying to learn from the training data how to predict or score, giving a new instance the chance of success. So you need some notation. PI star is a number between 0 and 1. It's the real life probability that I receives a positive outcome. This is like in the green gold world, the PI stars are always 0 or 1. In the red world, all the PI stars were a half. This is just like the true inherent probability. And everything that I'm going to say, it doesn't care. It's agnostic to whether probabilities are integer or arbitrary. And then the O's are always draws from Bernoulli distributions that have the P's as a parameter. So OI star is a Bernoulli draw from PI star, and this would be a real life outcome drawn according to real life's probability, assigned probability to individual I. Then we're also going to build models, and our models might be called F or they might be called P tilde. So Fi is the modeled probability, the one that our algorithm assigns to the instance I, the modeled probability that I receives a positive outcome. And OIF is a draw from the Bernoulli that has Fi as the parameter instead of PI star. Instead of truth, it has the modeled probability. So that's our notation. So one way of trying to talk about, yes. Sorry, let me find my arrow.
OI is
O stands for outcome.
is it 0, 1 valued?
Yes, it's always Bernoulli. I mean, it's a draw from a Bernoulli distribution. Okay, so one way of thinking about evaluating a scoring function, a predictor, is through this concept of what we call outcome indistinguishability. So this crowd is familiar with distinguishers. So distinguishers in this case are going to try to determine whether an outcome is drawn from real life, OI star, or whether instead it's drawn according to the model of the world given by F, so OIF. So our distinguisher gets as input a triple, the individual I, that's the instance I, the prediction made by the model, Fi, and an outcome. And it's trying to figure out, was this outcome drawn according to real life Pi star, or was it drawn according to modeled out, according to the model OIF? And so we say that a predictor F is outcome indistinguishable with respect to a collection blue A of distinguishers if no distinguisher A in blue A can distinguish real life outcomes from those drawn according to F. So pretty much what you'd expect. And when you look at things this way, you can then build a hierarchy, and the levels in the hierarchy actually vary according to the degree of access that the distinguisher has to the prediction function F. Like you might imagine that a distinguisher that had access to the code of F might be able to do a much better job of distinguishing than one that only had access to the outcomes and nothing else. So there are various levels in between, and we're going to be focusing on this one, which is the one I drew on the slide. So the distinguisher is given the individual, the prediction of the model, and an outcome. And it's just trying to say real life outcome, modeled outcome. So the goal is to design a function, a prediction function, that is indistinguishable from, that is outcome indistinguishable from real life. So that is to say that all of the distinguishers will fail to be able to distinguish whether this is a modeled outcome or truth. And the general idea is, there's a wonderful video on YouTube of Carl Sagan. Yes, Carl Sagan. No. Richard Feynman talking about how do you come up with a new law of physics? And he says, well, first you guess the new law, and then you compute its consequences. And then you design an experiment to see whether you match the consequences or not, whether the consequences are matching real life. So in this sense, we have this model F. It's telling you what the consequences should be. Can your experiments, the distinguishers A, distinguish that no, you're not actually predicting what's happening in real life. You're predicting something that looks completely different. So we want our predictors to pass those tests. And to make a long story short, outcome indistinguishable predictors can be constructed based only on real life outcomes data. And the way that this is done is you show that this is equivalent to something called multi-calibration, which was investigated and for which an algorithm was obtained by Aber Johnson, Kim, Reingold, and Rothblum. And it actually has interesting complexity theory roots that date back to Trevisan, Tulsiani, and Vadan in 2009. And so that's a very interesting, there are very interesting conclusions now that people are starting to investigate based on this connection to the TTV paper. So in this picture, what we're saying is that we start with the real life probabilities, P star, and we have an algorithm that is given access to samples drawn from real life. And I forgot to say also real life samples. So we get real life training data. And we can create from this a predictor P tilde that is outcome indistinguishable with respect to any collection of distinguishers. The algorithm that does this prediction never sees real life's probabilities because we can't get hold of them. We don't even know whether they have to be integer or not. You had a question?
Yeah,
The notion of indistinguishability, what?
I just wanted clarity on the notion of indistinguishability. Is that statistical or computational?
It's statistical.
Okay, thanks.
What? But it's against a specific class of distinguishers, but it is statistical.
I would call that computational,
Um,
but it's against the class of distinguishers.
sorry. Fine. But I'm not thinking, yeah, right, okay.
Because could be.
It could be. I'm sorry, you're absolutely right. Computational, except I don't think about it in these terms. I'm thinking about specific statistical tests.
Yeah.
And all we care about, like, we could have a huge, nobody said that, so first of all, the definition makes sense. Whether the class contains dumb distinguishers or smart distinguishers. And the only thing in like the sample complexity only cares about how many distinguishers or the VC dimension of the set of distinguishers. And nobody is talking about, very importantly, now nobody is talking about, say, the class A being the set of all polynomial size circuits or all circuits of this size or that size, because the sample complexity would be too large. So this brings up a very interesting question of what should the collection A of distinguishers be? And it doesn't have to be dumb ones, and which is why I said statistical. But ask me about that if there's time during the questions, because I have a lot more to not say, but there's a lot more to ask about that. Like, I have questions. Okay. So this stuff came up. I mean, even these questions are like, for me, what is the meaning of an individual probability? This all arose in the context of the theory of algorithmic fairness, which is a relatively new field that started, I guess, about 11 years ago. And then I think my attention on this particular question was focused by the work of Hebert, Johnson, Kim, Reingold, and Rothblum. And this particular direction of multi-calibration and outcome indistinguishability has really been blossoming in the last 2 years or so. And in fact, there was a workshop at the Simons Institute about, I don't know, 2 or 3 weeks ago, April 24 to 28, called Multi-Group Fairness and the Validity of Statistical Judgment. Now, that's interesting. And at the heart of it is a kind of view, which wasn't in the original algorithmic fairness paper, of accuracy as fairness. And in fact, the literature even calls PI star nature. Now, yes, we inherited this from the online guys, from the statisticians, but there's this sense of, it can't be changed. And that doesn't make any sense. So first of all, at best, you could say that the idea, if you really want to think about this as fairness, that the idea was to learn as much as you can and then adjust, maybe figure out how you should behave, how you should score, whatever, in an adjustment phase. But there's no real treatment of this. So the chance of success for all of us is contextual. This goes back to my feeling support from Russell, that it increases my chance of success that I feel supported by my community. And we know that in the workplace, you can have an egalitarian workplace in which women do succeed, and you can have a really misogynistic news company where women tend to leave and they don't succeed as much. So it's not that PI star is nature. We can even see in different companies that there are different probabilities of success. Your chance of success depends on your environment, whether you're accepted or not, whether you're supported or not. More deeply, even who we are is contextual. What you manage to achieve affects your view of the life that, and what you try to do in the future. What kind of air we have? Is it clean or is it dirty when we're growing up? What kind of water do we have? Education. What about our parents' connections, our healthcare that we're given? So all of these things also affects who we are. There's not like some inherent, this is who you, anyway. So this brings us to the notion that we're calling corrective transformations. And again, this is very new. This is really in its infancy. This is basically envisioning a better world. It's joint work with Omer and with Guy. So let's think for a minute about an ideal world, a utopia. So in utopia, we have individuals X, and they have some probability of success, U star of X. And in utopia, everybody is supported and given great health care, and we all do like the best we possibly could do. Okay, it's utopia. Don't worry about defining it too much. Real life doesn't look like utopia, right? There's racism, there's sexism, there's poverty, there's lack of reproductive health care, lack of gender affirming care, failure to be exposed to ideas that are in banned books, and privilege. And they all transform the ideal world to the real world in what amounts to some kind of transformation T from utopian U star to the reality P star. And in general, it's uninvertible. Right? Like you just beat stuff out of people. Tony. What if I'm having trouble hearing you. You're saying, what if there's one utopia?
One a utopia that we all agree on. Is it going to matter?
Just to help set our thinking. I don't need there to be just one utopia.
So this is like your utopia? Should I think of this as somebody's fixed ideal?
You should think of it as an ideal. And it's not going to show up again on any other slide. And just to say that, you know, we are deformed by the world that we live in. So the transformation, like I picture it as a transformation that takes an ideal world and gives us the real world, which is not as nice. But again, it's contextual. It would be different in different places. So we can't undo this. But it just, what we want to do is we want to be better than we really are. And in my mind, I think about this as taking a step toward the ideal or toward an ideal, to a better world. So let me define the notion of a transformed predictor. So let's say we have a universe U of potential individuals. And so a predictor, it could be real life. Real life is a predictor, could be something else. It just assigns to each individual this number between 0 and 1. So we can think of it as a giant vector of dimension size of our universe of people. And the transformed predictor operates, we have a transformed predictor that's going to give us a different vector of scores or predictions for people. And our transformation will operate on pairs X, P of X. Like we don't have our hands on P of X, but we imagine a transformation that could operate on pairs X, P of X. And this gives us transformed predictions. It's just a mathematical object. Okay? And so we're going to have this invariant here, that the transformation tau of P, the transformed predictor applied to X, is just this transformation T of X, tau of X, P of X. And it's mathematically well defined, even though we can't get our hands on P star of X. It's just a, right, okay. And in particular, we could also imagine that there is a transformation that operates on P star of X, P star, and that gives us the transformed reality, the better reality. So for example, in our transformed world, maybe the scores for the members of some population group G are going to be boosted. So that might look like add 0.2 to the scores of the members of G. It's a simple transformation. Formally, tau of P applied to X would be the minimum of P of X plus 0.2 and 1, because all our numbers have to be between 0 and 1. If X is in G, and for the members not in G, we just leave their scores untouched. So this is a transformed world. You might like it, you might not like it, you might think it's a great idea, you might think it's a terrible idea, but it is a mathematically well-defined notion. We could also imagine transformations that are parameterized. So we can introduce a learner that takes as inputs labeled examples from the real world and produces some parameters, pi, that are obtained again by studying the real life outcomes data. And an example of this could be that in the transformed world, scores for the members of some group B are adjusted to ensure demographic parity. meaning that the probability of a positive outcome, if we choose, in expectation over set A is the same as the probability for a positive outcome in expectation over group B. So the way we would do that could be to learn a parameter which is defined by the base rate in A under reality minus the base rate in B under reality divided by 1 minus the base rate in B, and set tau of P of X according to this equation. And that will ensure that on average in A, tau P of X is equal to on average in B, tau P of X. Technically, the transformed predictor may not be unique. And so we define something called the canonical transformed predictor, where it's really the expectation of a tau of P, where expectation is over a bunch of things. I'm never going to mention this again, but if you were wondering, that's how we deal with uncertainty there. So where does tau come from? For the purposes of this work, it's just exogenous. Maybe it comes from some combination of knowledge from experts and wisdom and ethics and policy and history and geography and arithmetic, machine learning and so on. But for our purposes, we just assume that it has been determined that tau of P star, which we're going to call Q star moving forward, would be a better world. Yes.
So has the direction of tau been reversed from previous slides? So before you were saying that tau is kind of a corrupting influence,
Great.
marring
No, let me show you
utopia.
the picture on the next slide. Okay.
Okay.
So here was our picture. We had utopia. We had this horrible transformation T that took utopia to the real world P star. And now we're defining a tau, which is trying to make things a bit better.
Okay.
So it can't invert tau, but it might take a step in a good direction. It might be something that could transform what would be happening in a misogynist work environment to what would happen in a better work environment. Tau is going in the other direction. So maybe T went from utopia to reality, and now we're trying to go in a better direction.
And T is totally unknown, but tau is.
We are going to define, but somebody has suggested a tau, and we're looking into it. Right. Good. So again, we're just going to sort of say tau has been given to us, and we have reason to believe it will be a better world. Maybe not the best world, but a better world. And what can we do? We don't have any data from this better world. So what could we do? And the question we're asking is, when can we build a predictor that's indistinguishable from tau of P star using only samples from the real world? Because that's all we ever get is samples from the real world. So again, we have P star, which is the real icky world. We have real life samples. We can use those real life samples to define a predictor that is outcome indistinguishable with respect to whatever set we want from P star. We'd love to do the same thing on the right-hand side, but we don't have any samples from this better world. So the OI stars are drawn from Bernoulli of PI stars. We have no Bernoulli of Q stars because there's no data from this better world because it isn't the real world. We have no way of getting our hands on it. So the question is, can we build something that would be indistinguishable from this better world using only samples from real life? Let me turn on my pointer. The only thing we have are these samples from real life. And we want to build something over here. The question is, can we do it, or when can we do it? In order to answer this, I have to introduce the notion of a random instantiation of a predictor. So remember that the predictor is assigning numbers between 0 and 1 to each element in the universe. A random instantiation is like real life. Like we define P prime X to just be a draw from the Bernoulli distribution that has probability P of X. If I did this multiple times, I might get different values, or I might not. But certainly the notion of a single random instantiation makes sense. Notice that if P itself is always Boolean, then all random instantiations are exactly P. But if P is not Boolean, then random instantiations can vary. If P of somebody is a half, then some of the random instantiations would have 0 for that person, and some of them would have 1s for that person, about half of each. And the key property is for being able to build something that is indistinguishable from the better world is the question of robustness of the transformation to random instantiation. So intuitively, does tau of P look like what we would get if we first did a random instantiation of P to give ourselves P prime, and then saw what that did. So as an example, here on the left, P of X, let's say, is some value V. Let's suppose it's not integer. It could be integer, but let's suppose for a minute that it isn't. Then if I draw my first random instantiation, maybe I get some value U1. It'll be Boolean. I don't know what it is. But do the second instantiation, I get a value U2, again, Boolean, U3, and so on and so forth. And I know that on average, because these are random instantiations of a Bernoulli variable with probability P, on average, their values will be V. Right? Now, let's look at tau of P. Tau of P is some other number V prime. Again, maybe integer, maybe not integer. So tau of P applied to X is some other number V prime. It's the value that is assigned to X in the transformed world. And I can look again at random instantiations. If I look at, I take a random instantiation of P and I look at what happens to X under this random instantiation. Well, the first time I do it, I get some number U1 prime. The second time I do that, I get a number U2 prime, and so on and so forth. And what I want to know is, will those random instantiations in the world on the right after the transformation, will those random instantiations also in expectation have a value of V prime or not? If they always do for all P and for essentially all X, then tau is robust to random instantiations. And otherwise, tau is not robust to random instantiations. So let's look at our two examples. This is the one where we were boosting the scores for the members of G. So if you were in G, your score got boosted by 0.2, but capped at 1. And if you weren't in G, your score stays the same. So this is not robust to random instantiation. Why? Suppose we look at members X whose value under P is a half. So if I look at the random instantiations, about half of them are 0 and half of them are 1. That's what it means for P of X to be a half. But in the transformed world, when I look at a random instantiation over here, P of X is a half. When I add 0.2 to that, I get 0.7, no problem. But if I take the random instantiations and look at tau P prime of X, those are going to be numbers that are either 0.2 or 1, not 0 or 1. Why? Because we can't add 0.2 when the score is already 1, so that's capped at 1. When the score is 0, we can add 0.2, and so we get a 0.2 there. And those guys don't average to a half, they average to probably 0.6. Okay? So this is not robust to random instantiation. In contrast, the demographic parity example is robust to random instantiation. And roughly speaking, the reason is that with this particular transformation, with high probability of random instantiation of P yields about the same values for the learned pi. Yes?
Slide real quick.
Yeah.
So you said it didn't average to half on the right, but it should have averaged 2.7. Is that what you were?
It is, yes, it should average to 0.7.
Okay, because
Right, your random instantiation value.
should have been
average to
0.7, but it's 0.6.
Mhm.
Okay, good. Because you said 0.5.
No. Sorry, I misspoke. P of X gets mapped under tau.
Right.
To a half plus 0.2, which is 0.7.
Right.
If I look at random instantiations and apply, if I look at the random instantiations for P prime,
You get 0.6.
I get 0.6.
Yeah. So
And
this
that's
the
not-
discrepancy between 0.6 and 0.7, but
Correct. That's the discrepancy that
Okay.
bothers me. Right.
Okay.
Okay. Thanks. Okay. Good. So the theorem that we show is that robustness to random instantiation is a complete characterization. So informally, what this says is, remember that sometimes we're learning parameters, and that's what the learner L is. So if this pair L and tau is robust to random instantiation, then there is an algorithm M for learning something that is outcome indistinguishable from Q star, from this better world, for any set A of sample access or no access distinguishers. If L tau is not robust to random instantiation, then there is a particular no access distinguisher A, so that there is no algorithm that can learn a predictor that is outcome indistinguishable with respect to A from Q star or tau of P star. Yeah,
So this robustness is not just equivalent to being linear or something like that? To being linear or no? Linear. Okay.
so I have about 4 minutes left or something. So I'll give you just a little bit of 3 minutes left. Okay, just a little bit of the flavor for sufficiency. It's going to use lots and lots and lots of samples. So we get a ton of samples from real life. We're going to take these samples and we're going to partition them into blocks, some number L of blocks. And now we're going to view each block individually. So forget about all the other blocks now and just look at the first block over here. We're going to view these as samples from random instantiation of P star, which is fine. That's because we can't tell the difference between, you know, I mean, that's just what they look like. Like they are even if there's uncertainty, these are draws from Bernoulli distributions, and this is what they look like. So that's what we do with these. We view these as samples from one random instantiation. Then we view the next block as samples from another random instantiation, and so on and so forth. As long as no individual X shows up more than once, this is absolutely fine. We have to be a little bit careful if there's an X that shows up more than once, but that's very, very unlikely to happen. And so we don't have to worry. The proof takes care of it. Now, given more samples, when given a sample X, Y, Y is Boolean, it's a sample from real life. We choose uniformly one of our copies. Oh, sorry. So I viewed these as samples from one instantiation. I use that to learn a set of parameters, as if I'm going to now look at tau p pi 1 of like one transformation. My next block of samples I use to build another instantiation. These are transformations of different random instantiations of P star. And I do this and I get L different transformations on random instantiations of P star. Now I have a sample. My job in life is to create samples that look very much like they're coming from the world Q star. If I have samples from Q star, I can then turn the crank and take samples and turn them into outcome indistinguishable predictors. So what am I going to do? I'm going to say, okay, you gave me a new sample from real life. I'm going to choose uniformly one of these predictors, transformations that I've computed. I'm going to see what I'm going to view Y as itself a random instantiation of P star of this X, and I'm going to set Pj of X, the jth predictor, to have an outcome of Y. And then I see what does the transformation do with that? Because the transformation operates on X, Y. On X, P of X, but in this case, P of X is Y because it's a random instantiation and it's an integer. And that gives me this value. And then I draw really from that, and I get X and Z, which is a sample from a randomly chosen L, a randomly chosen copy of tau pi j of Pj of X. Now, why is that good? So I've gotten all of these random samples from these different transformed things. Now is where we have robustness. Robustness says that on average, if I choose a random instantiation and I look at the transformed predictor for that random instantiation, on average, that looks like Q star of X. Yay, that's what I want. I want samples from Q star of X so that I can then take the thing that takes samples from a reality, in this case it's Q star, and it produces something that is outcome indistinguishable from that reality. But that's the intuition for why that works, and that's the end of my time. So I have one last slide. Well, actually two last slides. So next steps. This is just the first work in a rapidly expanding literature that tries to consider predictions for a better world, not the existing world. And we have this complete characterization in an algorithm. So it would be good to understand what are the transformations that actually satisfy this condition? What can we do with them? We can also use this as a way of exploring different ways of scoring and seeing what they do. And I do wonder what happens, I don't know, at higher levels of the hierarchy. Finally, my favorite thing that has been said about Russell, I would like to channel Stephen here. And Stephen has a great love for Russell that has always been clear. And the way he speaks about Russell in hagiographic terms, all of which are appropriate. And what Stephen said about Russell is a subtle guy. So thank you.